Now we will calculate the MLE, the maximum likelihood estimation for the Poisson mean. Okay, so the for example, we have yi, okay, which is equal to y1, y2 up to yn. Okay, it follows Poisson distribution with a mean of mu. Okay, this is the response variable. Okay, so the by likelihood function, we have capital L of theta, where theta is the parameter that we are interested in. Okay, so it is equal to the multiplication for I is equal to 1 up to n e raised to power minus mu. Okay, mu raised to power yi divided by yi factorial. So if we take the, as we are interested in the log likelihood, okay, so we take the log of this capital L theta, which is equal to log of this multiplication of, okay, this is p the probability that y is equal to x or k, or okay, or in this case, in this particular case, it is equal to y is equal to small y. Okay, capital Y is equal to small y in this particular case. Okay, so if we take the log, okay, so we know that log actually changes the multiplication into addition and the division into subtraction. Okay, so by taking a log of capital L, it becomes small l. Okay, theta, this is the parameter. Okay, theta can be anything, it can be beta naught, beta 1, anything. Okay, it can be any parameter. So by taking log, it's changed into summation. Okay, so summation into log of these two are multiplications, so we will it will become addition and minus log of this. Okay, so log of e raised to power minus mu plus log of mu raised to power yi minus log of yi factorial. Okay, so we have the parameter we are interested in is mu in our case. Okay, so small l of mu, okay, it is equal to summation of I is equal to 1 up to n. Okay, so this will give us minus mu into log of e plus yi into log of mu minus log of yi factorial. Okay, so the final answer that we will get for the log likelihood function, okay, it will be equal to small l of mu. Okay, it is equal to summation for I is equal to 1 up to n. Okay, so minus mu plus yi into log of mu minus log of yi factorial. Okay, this is the log likelihood function for the mean mu. Okay, now if you want to find the or estimate beta naught and beta 1. Okay, so what we do is we partially derive this log likelihood function with respect to beta naught and with respect to beta 1 to find or estimate both of these. Okay, so that is the solution method in order to find or estimate beta naught and beta 1. Now suppose we have an example, okay, to solve based on Poisson regression. Okay, so the variable that we are interested in, okay, the count data is the number of accidents. Okay, so let's suppose capital Y it is equal to the number of accidents, number of road accidents. Okay, and we have an explanatory variable x, which is the traffic volume, for example. Okay, so we have two things over here. Okay, we have the response variable y, which is the number of accidents per day, for example. Okay, and we have an explanatory variable which is the traffic volume that day. Okay, and we are given that the log of mu, okay, it is equal to 0.4 plus 0.2 into x. Okay, x, we know that it represents the traffic volume. Okay, so if you recall the Poisson equation, okay, so the log of mu, it was equal to beta naught plus beta 1 into x1. Okay, in linear form. Okay, so if we compare both, for example, this is a and this is b, so if we compare a b, okay, and correspond it, okay, so beta naught here is equal to 0.4 and beta 1 is 0.2. okay, and x is the explanatory variable. Okay, so the very first thing that we need to find, the part A of the question says that write the mean function. Write the mean function. Okay, part B asks us to interpret beta 1. Okay, and part C says to find the value of mu when x is equal to 5. Okay, so let's start the solution process. Okay, so the very first part of the problem is to write the mean function. Okay, so by Poisson regression, we know that mean is the exponential of the beta naught plus beta 1 x1. Okay, or beta I xi in general form, mu I. Okay, so we have mu is equal to, now we have beta naught is equal to 0.4 as we corresponds these two equations a and b. So we find that beta naught is equal to 0.4 and beta 1 is equal to 0.2. So putting these two values over here, okay, so we get e raised to the power 0.4 plus 0.2 into x. Okay, so this is the mean equation, mean function. Okay, now the part B asks us to write so interpret beta 1. Okay, by this interpretation we actually mean that what will be the expected increase. Okay, let me write it over here. Okay, interpret beta 1. Okay, which means that what will be the increase in number of accidents if we increase the traffic volume by 1 unit. Okay, so beta 1, this is the slope. Okay, and this slope actually corresponds to the change in y with respect to x. Y is the number of accidents and x is the traffic volume. Okay, so the change in the number of accidents, okay, per unit change in the traffic volume, okay, that corresponds to the slope, which is beta 1. Okay, and by equation we also have we can relate it as, because beta 1 is the coefficient of x1 or x. Okay, so this explains the relationship of y, which is the number of accidents, okay, with capital X, which is the traffic volume. Okay, so in order to interpret that, what we need to do is we need to find e raised to power beta 1 value. Okay, so to find that we put the value of beta 1. So beta 1 in our case is 0.2. Okay, so e raised to power 0.2 gives us a value of 1.22. Okay, now this 1.22 means that if we increase the traffic volume by 1 unit, the number of accidents, okay, increases by 22%. Okay, so that is the interpretation of beta 1. Okay, now coming to the part C, which actually asks us to find the expected count. Okay, find the expected count. Okay, and by count we mean the road accidents when capital X is equal to 5, when the traffic volume is equal to 5. By 5 we can mean like 5,000 or 5 million or whatever. Okay, whatever the traffic volume is, okay, by any unit. So for that, what we need to do is, okay, we have an equation for the mean, which is equal to mu is equal to e raised to the power beta naught plus beta 1 x1, okay, or x. Okay, so putting the values of beta naught and beta 1 and x here, so we get e raised to power 0.4 plus 0.2 into, what is the value of x? It is equal to 5. Okay, so e raised to power 0.4 plus 1. Okay, so e raised to power 1.4, so it will approximately give us 4 or 4.1 maybe. So the number of accidents when the traffic volume is 5 is 4.1 or 4 maybe. You can round it to 4 or 4.1. The actual figure is 4.05. Okay, so there are 4 accidents when the traffic volume is 5. Okay, that is the expected count at x is equal to 5.